Hello. We are continuing with our college algebra lectures. This is lecture 6. We are still in the prerequisite section. So this is mostly just a review for college algebra. So you can use this as a primer if you are taking a college algebra course. And this is probably maybe the most important of the sections that we're going to cover. Polynomials is pretty important, but factoring is very, very important. We'll be using it a lot during the course. So it's something you want to have a handle on. We are going to cover different kinds of factoring. The list here: greatest common factors, trinomial factor, factor by grouping, factor of perfect square trinomial, differences of squares, sum and difference of cubes, and then look at, lastly, factoring expressions where there's fractional or negative exponents, sometimes called rational exponents. So let's begin. The first thing we should look at is, what is factoring exactly? When we say we're factoring something, what do we mean? Well, let's think of a number. So consider the number 36. We can break 36 up into its prime factorization. So one way to do that is to make a tree. 36 is 6 times 6. 6 is 2 times 3. 2 times 3. So we can write 36 as 2 times 2 times 3 times 3. Of course, we can also write it as 2 squared, 3 squared. So this is the prime factorization of 36. It's the factors that make up 36. So there's an analogous correlation here to polynomials. We could factor polynomials the same way we'd factor numbers. Now, the notion of prime isn't something we have, but reducibility, and that will come more in the course. But for now, let's look at some technique to factoring, breaking up a polynomial into its factors. So let's look at the greatest common factor. The greatest common factor is the first thing you always want to look at when you're factoring a polynomial. You want to look at all the terms of the polynomial and see if they have anything in common. Now, if you need a review of polynomials, see lecture 5. I'll put a link to it here. So we're going to assume you understand what a polynomial is. So here's our first example: 2x squared plus 4x. That's a polynomial expression. Now we want to take out what they have in common. So what do they both have in common? So let's look at the coefficients first. We have 2 and 4. And we can see that 2 divides 2, 2 divides 4. So what they have in common is 2. Now, what about the variables? Well, the first term has an x squared, the second term has an x. So the greatest common factor for these two is x. So that means that what they have in common, the greatest common factor, we'll say GCF, is 2x. So I could take a 2x out of both of these terms. So what do we mean by that? What do we take out of? Well, it's essentially a division. If I have 2x squared and the greatest common factor here is 2x, I'm dividing this. And this leaves us with x. The same with 4x. I'm essentially dividing it by its greatest common factor, which leaves us with 2. So when we take out, so to speak, a 2x, we are left with x and we're left with 2. So that's the greatest common factor being pulled out of 2x. Now, is this correct? You can always check by multiplying back. So what I mean is you can distribute to see if you get the original expression. So 2x times x is 2x squared. 2x times 2 is 4x. And that was indeed our original. So this is a factorization of this binomial. If you need to review again of polynomials and multiplying, adding, subtracting polynomials, look at the previous lecture, lecture 5. Let's look at something a little more complex. We will run through a lot of examples in these lectures. There are rules, of course, and theorems and corollaries and lemmas, but examples of these terms, these definitions, these lemmas, corollaries, theorems are always valuable. So here is a polynomial expression, 30x cubed y minus 45x squared y squared plus 135x y cubed. So what we want to look at is what they have in common. So let's look at the coefficients first. We have 30, 45, and 135. We'll ignore the negative. We'll just keep it negative. Each of these is divisible by 15. So the greatest common divisor, but we're using factor, for the coefficients is 15. Now the first term has x cubed y, the second term has x squared y squared, and the third term has xy cubed. So the greatest common factor, let's look at these separately. Let's look at x's first and then y second. So the first term has 3 x's, right? X cubed is x times x times x, x squared is x times x, and the last one is just x. So that means they all have an x in common. Usually you're going to take the lowest power of variable. So here the lowest power is this 1, so we're going to take a 1 out. Because if we divide x by x cubed or x squared, we're going to get a negative exponent. So we want to make life easier, so we don't want negative exponents where possible. Now the same thing with y. We have a y here, y squared, y cubed. So the lowest power is 1, so we have xy. So that means our greatest common factor is 15xy. So we're going to take 15xy out of each term. I'm going to write that out here. So 30x cubed y. Let's do these really quick on the side, and we'll do each term as a division. So obviously 30 goes into 15 2 times, or 15 goes into 30 2 times. X cubed, x divided by x leaves an x squared, and y divided by y just leaves 1. Now negative 45x squared y squared divided by 15xy will leave us with negative 3, because 45 divided by 15 is 3. Negative x squared divided by x leaves an x. Y squared divided by y leaves a y. And lastly, 135xy cubed divided by 15xy. Now 135 divided by 15 is 9. X divided by x is 1. Y cubed divided by y is y squared. So 15xy taken out leaves with x squared minus 3xy plus 9y squared. And that's a factorization. Usually when we are left with the parentheses, we want to see if that's factorable. The inside, there's nothing left that we can take out GCD-wise or GCF-wise. We'll get into other techniques in this lecture. And then we ask the question, are we done when we are looking at an expression? We keep factoring until we can't factor anymore. And if you need a little bit of refresher on exponents, see our previous lecture on exponents. Again, I'm going to have to assume that you know some stuff. So let's move on to trinomial factoring. A trinomial is a three-term polynomial. It has three terms, usually of the form. Now we're going to do two different forms here. We're going to do the first one, we're going to do, say, x squared plus bx plus c, where b and c are just real numbers. And we're going to assume that there's a 1 in front of x squared. So this process is essentially reverse foiling. We foiled in the previous lecture is a form of multiplication, multiplying two binomials. Now we're going to look at how to undo a foil. In other words, how to factor a trinomial. So we want essentially x squared plus bx plus c to equal two binomials. And when the first term is x squared, we can assume that we have x and x in the first position. So the technique here is we have a little handy table. And the way we do this is we want to multiply two terms that will equal our c term, that when we add them, equal our middle term or b term. So we list the factors, and then we add them. We're going to have multiple lists of factors of c if c is not a prime number, and combinations of positive and negative depending. And then we're going to add those and then see if they equal b. When they equal b, we found our factorization. All right, so that's a lot. So let's look at an example. We have x squared minus 7x plus 6. So we want to factor this, and we want to use the technique we just looked at. So conceivably, we should be able to factor this into two binomials. And again, x squared is x times x. Now, to get the outside terms, what we're going to do is we need two numbers that multiply that equal 6. Then we add equal negative 7. So we can really just quickly list some factors. If for 6, it's not too hard. We need it to be positive. So 6 times 1, negative 6 times negative 1, 2 times 3, and negative 2 times negative 3. So those are the factors of 6. Now I'm going to add those. So in other words, I'm going to add 6 and 1. I'm going to add negative 6 and negative 1, 2 and 3, and negative 2 plus negative 3. So this is 7, negative 7, 5, negative 5. So we want it to equal negative 7. So that's our guy right here. So that means we put negative 6 and negative 1 in here. That's the factorization. Now, if we want to check it, we would FOIL. So we get x squared minus 6x plus 6, which is x squared minus 7x plus 6. So that checks out. So that's the factorization of x squared minus 7x plus 6 is x minus 6, x minus 1. Two binomials. So that's handy, undoing FOIL, factoring. Let's look at a case when our leading coefficient from our leading term is not 1. So an example is 6x squared plus x minus 1. Now let's look at a form of a quadratic. Ax squared plus bx plus c, where a, b, and c are any real number. And the first thing we're going to do with this method is we're going to take out our a, b's, and c's. So a here is 6, b here is 1, c here is -1. So what we want to do first in this case is find factors of AC. So AC is 6 times -1, so -6. So we want factors of -6. Two, -3, -2, 3, 1, -6, and -1, 6. So we're going to sum these. So 2 plus -3 is -1. -2 plus 3 is 1. 1 plus -6 is -5. And -1 plus 6 is 5. Now, what do we want this to equal? Well, we want it to be equal to b, or in this case, equal to 1. So if we looked at the chart, it would be factors of AC that equal b. So multiplication and addition. So what we have here is -2 and 3. So what we do is we put an x to each of these terms. So -2x and 3x. And this technique, this grouping technique, is we're going to add them. And then we're going to have our 6x squared and our -1 out here. So we essentially broke up that middle. The middle was, remember, x. So we broke it up between -2x and 3x. And the reason we're going to do that is we're going to group them. Now I'm going to group the first 2 terms, and then the second 2 terms. And then we're going to factor the greatest common factor from each term. Not from the total, but from each term. So I'm going to look at what 6x squared and 2x have in common, and that's 2x. That leaves me with a 3x and 1. And then we have a 3x minus 1 over here. Now you can tell we did this in such a way that we are left with this 2 binomials that are exactly the same, and that's on purpose. So we're factoring out the GCF from the entire expression. So if we think of this as being in parentheses, the first term is 2x times 3x minus 1, and the second term, we can think of this as being 1 times 3x minus 1, if that's easier to conceive. So they both have 3x minus 1 in common. So I'm going to bring out a 3x minus 1, and I'm left with a 2x plus 1 afterward. So that's a factorization when we have a number in front of x squared that isn't 1. So let's write this down. So this is what was factoring trinomials by grouping. So we can write down the algorithm, and this will have the form ax squared plus bx plus c. So the first thing we did was we listed the factors of AC. Next, we found we'll call it P and Q, that are factors of AC. That add to B, or P plus Q is equal to B, and P times Q is equal to AC. So those two things have to be simultaneously true. The third thing we did was we factored the GCF of each term well, nope, I skipped a step, didn't I? The third one is where we have to group these. So we rewrite as ax squared plus px plus qx plus c. So in other words, the p we found in the previous step, we're going to add the x or multiply the x to it and then put it in the middle of our equation or our expression. And then we group and factor the greatest common factor from each term. Five, we factor the greatest common factor of the expression itself. So once we've done the GCF of each term, then we do the GCF of the expression. And that's how we handle where A is something other than 0, or 1, would say. A is always non-zero, but if A is not 1, then this is the method we can use, which isn't too bad. It allows us to factor rather quickly. Another method, when I learned this years ago, was what's called trial and error, which is essentially doing the same thing. In the case where we had 6, I learned to write all possible combinations of this. And you can see how this gets kind of unruly, and then just do a sort of guess of factors of the last term. So this is more of an algorithm that works every time. The guess and chug method is not great. So I suggest getting comfortable with that. Sometimes you can just see it. Most of the stuff, when you do it enough times, you will look at a polynomial and sort of suss out the factorization. All right, so next we're going to talk about factoring. Perfect square trinomials. And these have a particular form that allows us a sort of shortcut. So the methods that we just learned work on these. These are just sort of shortcuts that are really handy for a quick factorization. So I'm just going to write down the rules first. So these are the two rules. A squared plus 2ab plus b squared, we can factor to a plus b squared. And a squared minus 2ab plus b squared, we could factor to a minus b squared. Now, what does that mean? Well, again, it's determined by the polynomial look. And what do I mean by look? It's when you have a square, that's what I mean by perfect squares, of the first and last term. If I were to take those terms and square them, they would equal 25x squared and 4. In other words, is this perfect square? Well, I know I can write this 25x squared as 5x squared, and I can write 4 as 2 squared. So in our above form here, that means that we have a is equal to 5x and b is equal to 2. So all we really need check now is this is a positive. So we have to see that does 2ab equal 20x? If it does, then we have this form. We can use a plus b squared. So 2 times 5x, that's what a is, and b is 2, equals 10x times 2 equals 20x. So that means that this factorization is just 5x plus 2 squared, meaning it's a perfect square. 5x plus 2 squared is our factorization. Again, the middle part you can kind of see just from the fact that we have 5x times 2 times 2. You don't necessarily always need to write this down, but as you're learning, it's good. It's good to write. You can never write too much. I suppose you could write too much, but when you're starting, write out as much as you need to write out to feel comfortable. Now, if you're in a class and you're handing this in, maybe be more strategic about what you hand in, but most professors like to see work. I know I do. I also like to see how people think, so it helps to write out. So is this perfect? Well, we know we can write this as 7x squared, where a is going to be 7x. And 1, well, 1 we could always write as 1 squared. Kind of cheating, but that's how it is. So that's b is 1. Now, 7x times 1 is 7x times 2 is 14x. So yes, we can use this form because the middle term works. So that means we can take 7x and it's minus 1 squared. It's a factorization of 49x squared minus 14x plus 1. So that's a handy thing to do. You can, again, you can use the previous grouping factorization method to factor 49x squared minus 14x plus 1. It'll take you a bit longer, but it'll work. Let's look at something called factor the difference of squares. Ooh, keep hitting the erase button. And now I'm not. Okay. So again, this has a form. If I have a squared minus b squared, I can always factor this into a plus b, a minus b. So it becomes an identification problem again, where I just have to look to see if I have the necessary conditions met. So 9x squared minus 25. Now, do I have a square and a square? Well, this is equal to 3x squared. And 25 is equal to 5 squared. So yes, so a here is 3x, b here is 5. So I should be able to factor this between 3x minus 5 and 3x plus 5. And again, if you want to check, you can FOIL. FOIL will always tell you if you are correct because what you multiply back should equal the original polynomial. Next, let's look at something called the factoring of the sum and difference of cubes. The sum and difference of cubes is again a form much like we just went over, or a cubed plus b cubed. If we have this particular form, it tells us that we can factor this way. And if we have a squared minus, or a cubed minus b cubed, we can factor it this way. So you notice that in the top, we have an a plus b, and then a squared minus ab plus b squared. And the bottom, we have a minus b, a squared plus ab plus b squared. Something you should memorize if you're good at memorization. Otherwise, keep writing it down. It'll sort of stick. So let's look at an example. We have x cubed plus 343. So we just need to identify if the first and second terms here are indeed cubes, right? So obviously x cubed is a cube. So our a here is x. But what about b? Well, 343 is 7 cubed. So we'll say that b is 7. So that means that we can factor this by the first form. We can take a plus 7 times x squared minus 7x plus b squared is 49. Now, we would ask ourselves, can we factor x squared minus 7x plus 49? What we have right now, what we've just learned, no. We're going to say we're done. There's other ways we can look at that quadratic, but for now, let's just say we're good. All right, let's look at another example for the other form. 27y cubed minus 8. So again, this is an identification. Can we write 27y cubed as a cube? And there shouldn't be any shock that 3y to the 3 is that. And so that means that a is 3y. And we can write 8 as 2 cubed. So that means that b is 2. So we put it into our second form, which means that we have 3y minus 2 times, now we have 3y squared, right? So that's 9y squared plus ab. So ab is 6y. And then b squared, which is 4. Well, that's a factorization. Again, we would ask ourselves if 9y squared plus 6y plus 4 is factorized. We're going to say yes for now. We can always look at that a little bit later in the course. So now we are going to look at factoring expressions we'll say with rational or fractional exponents and or negative exponents. So what do we mean? Again, if you need to review, go back to lecture 5 or 3. Negative and fractional exponents look like this. So the video on exponents, you can learn how to handle these. All the rules are in those videos. So I'm going to assume you know that. So let's look at an example. 2x to the 1/4 plus 3x to the 3/4. So we can still factor this. Remember, x to the 1/4 is the same as saying the 4th root of x, and x to the 3/4 is the same as saying the 4th root of x cubed. we're not going to write it that way. It's much easier to look at it as fractional exponents. Now I want to use the same rule for these powers. I'm going to use the smallest power. So I know 1/4 is less than 3/4. So I'm going to think that the greatest common factor of the variables is 1/4. So what we'll do here is we'll divide each term by x to the 1/4 and see what we get. So remember that when I have a denominator, same base x, I just subtract the exponents. So this becomes 2x to the 0, which is 2. Now what about 3x to the 3/4? Divide by 1/4. This becomes 3x to the 3/4 minus 1/4. What's 3x minus, or 3/4 minus 1/4 is 2/4 is 1/2. So this is equal to 3x to the 1/2. So it means the factorization is when we take out an x to the 1/4, what are we left with? We are left with 2 and a 3x to the 1/2. All right, let's do something a little more complex looking. The rules are the same. The exponents, the way we handle them are the same. So trust your rules. To write something ugly, 5x minus 1. This is a quantity to 3/4. We're going to add that to 7x times 5x to the negative 1 to the negative 1/4. And we want the 5x minus 1s to be the same base so that we can handle this exponent. So we want to factor from each term what they have in common. Now, what's the smallest power here? Well, negative 1/4 is smaller than 3/4. So let's say that we have the greatest common factor here is 5x minus 1 to the negative 1/4. So let's look at each term separately. And at some point, you are going to not do this step, this intermediate division step. Now, I'm not saying you're going to do it in your head, but you can basically just subtract the powers and get to the same spot. But I just want to illustrate what's happening. So when we divide that, we're doing 3/4 minus 1/4, which is the same as 3/4 plus 1/4, which is the same as 4/4, which is 1. So the first term leaves us with a 5x minus 1. 7x times 5x minus 1. Sometimes I just miss the button. The negative 1/4 divided by 5x minus 1 to the 1/4. This becomes 7x. This is negative. 5x minus 1 to the negative 1/4 minus 1/4, which is the same as negative 1/4 plus 1/4, which is 0. Anything raised to 0 is 1. So this means that we have 7x times 1, or just 7x. All right, so that means we factor out a 5x minus 1 to the negative 1/4. And what are we left with from the first term? 2, 5x. Yep, I wrote 5 and I was thinking 2. So 2, 5x minus 1 plus 7x. Now that's the factorization. We could maybe make the inside prettier if we want. Why not? Distribute that, we get 10x minus 2 plus 7x to make that even prettier, we have 5x minus 1, so negative 1/4. 10x plus 7x is 17x minus 2. So there's a factorization of that ugly polynomial. And in math, sometimes pretty stuff is better. Sometimes it doesn't matter. But that is generally a factoring strategy. We did some examples and some methods. But what you need to do with factoring, especially if you're new and just beginning, is to do a lot of them. Factor a lot of expressions, factor a lot. Use different techniques, explore which ones make more sense to you, whatever method you're using, and then check. Foil back, multiply, distribute, just to check to see if you are getting what you need to get. So that ends this lecture 6. Hopefully, I didn't go quickly and everything made sense. If it didn't, please leave a comment and I can address that. And the next lecture, lecture 7, will be on rational expressions. Rational expressions are, example would be 2x over y cubed plus x over z squared. Basically fractional polynomials. That's what we'll handle next in the continuation of this lecture series. And the next lecture will be the last lecture of the review section. And I think lecture 8 will be the beginning of the actual college algebra lectures. So hopefully you can be able to tune into those, and we'll see you next time. Like, subscribe, comment, do whatever. Appreciate it. Have a good night.